ECON 515, somehow all the courses related to mathematics and given by the Department of Economics, they bear the same title, Mathematics for Economists. So this also has that title. Now today, we actually will deal with just with the 0th chapter, which is about what the relationship between economics and mathematics is and what the aim of this course is. So we'll discuss that together. But it's good, since it's recorded, if you go back to this first session at the end of the semester, it will be more meaningful, I guess. And you can also test whether we reached our aim or not. But before starting with that, let me give some information, which is also included in the syllabus, which I gave. Now, we have 3 hours per week. Now, the first hour, the 8:40 hour on Tuesdays, that's the spare hour. So we will regularly use the second hour, this hour on Tuesday, and the 2 hours from 10:40 to 12:30 on Thursdays. But if we somehow miss some classes, then we'll use to make up for that the spare hour, which is the earliest session on Tuesdays. Now, you will have weekly homework starting from the next week. Well, so you will have around 10 or 11 homeworks, either 10 or 11, around that. Now we have to specify some conditions which will be required for being allowed to take the final exam. Well, in this course, it's a minimal requirement. Well, you should hand in at least half of the homeworks. So that's easy to meet. And regarding the homeworks, well, when you get back the homework graded, that will have 2 different grades on it. One is a number out of 10. Now that is to indicate how many points, how many marks you would get in an exam from the solution presented, if you present that in the exam. But that has no importance concerning the letter grade. Then you'll have a letter grade there. Well, 3 possibilities: S, satisfactory, N, neutral, U, unsatisfactory. Now, S corresponds to 2 points, N corresponds to 1 point, and U corresponds to nil, no points. Now, the idea behind that is you can, of course, discuss the homework problems among yourselves, but whatever you write and hand in, that should be your own product. If there is a perfect solution which is reproduced the same way by the whole class, everyone will get a 10, but that will be accompanied by you. Well, if you, depending upon the difficulty level of the problems, well, if you have 8 points, for example, that will correspond to S, which is full grade. So it is just to encourage you, to provide incentives that you actually, eventually, in the final step at least, that you work on the problem and do that. As I said, you can discuss that among yourselves. There's nothing wrong with that. But you should internalize the solution you hand in, because that's what will help in building up the knowledge, the competence, and whatever output is required is expected from homeworks. Then we'll have 2 exams, 1 midterm and 1 final. The midterm will be 35%. final 40%, and homeworks, they will be 25%. So that's quite a lot. So you should actually put weight on doing homeworks. My office hours, they will be on Wednesdays from 12:40 to 2 p.m. But this week there will be no office hours. Please note that. Well, in case that happens, I will let you know in advance. But you can also come to my office outside office hours, or, in order not to waste time, you can get into touch with me and we can arrange special appointments. So this is just when I will be surely in my office. Outside that, we can also have discussions. Well, I guess, and you will also get exercise sets. They will actually range from very easy questions to quite difficult ones. Well, for some questions, you will just read the question and you know what the answer is. Well, with some, that's not the case. The intermediate ones, they're the natural candidates to occur in an exam. So I also advise you to go through all the exercise sets, and that will be helpful because you can test your knowledge just by doing mathematics, by solving problems. If you can solve problems, if you can develop approaches which will helpful in solving the problem, and if you can actually carry out that plan to the end, that's what it's all about. Well, so these are actually the rules of the game that we'll be playing this semester together. Any questions about the rules? Okay, if you have any questions further, well, then we can discuss about that as well. Now, let's decide about which one of these will be open book with memory aid sheet, closed book, or so on. Let's leave that open for the time being. We can discuss about that later. So, chapter 0, that's always introduction. Well, when you ask what the relationship between mathematics and economics is, well, one of the most obvious aspects is, that in economics, no matter what kind of agent you consider, be it a consumer, a producer, a public authority, a regulatory authority, or something, whatever that is, they optimize something. Consumers try to optimize, maximize preferences or utilities. Firms try to maximize profits. Governments, public authorities are supposed to try to maximize social welfare, or if some fixed level of production is given and the technology is given, then the firm will try to minimize expenditure. Sometimes consumers put more weight to minimizing this utility rather than maximizing utility, and so on. So we have optimization problems, and if you're to optimize, maximize, or minimize something quantifiable, then, you have optimization problems. But these optimization problems are most of the time constrained. That is, if you're a consumer and if you wish to make a consumption plan which maximizes your utility, then you're bound by your budget constraint. Well, in production, you have feasibility constraints. Well, for public authorities, there might be some legal constraint, well, which has to be satisfied. So we have optimization problems, and almost all the time, they're not free maximization, minimization problems, but they're optimization problems under constraints. So in mathematics, we have rather powerful tools which tells us what kind of objective functions, under what kind of constraints allow solutions. Because when in mathematics you formulate a problem, well, the first question is, does there exist a solution? The existence problem? Well, what naturally follows that is, well, if there is some solution, is it unique? So existence and uniqueness solutions and methods how to find them, we have powerful tools in mathematics for that, and well, that's one big relationship between the two concepts. But here, within the same economy, you have different agents. And each agent is trying to solve his or her optimization problem. But the question is, if they all solve their own individual problems, can the outcomes be carried out simultaneously? Now, for example, if you consider a pure exchange economy, where the only kind of agent is consumer, no production, well, given some prices, I might make an optimal consumption plan for myself, which actually includes, say, buying 5 kilograms of bananas. But if there's no one who offers that, then I cannot carry that out. So we have, in economics, several interdependent optimization problems, which mostly will be solved simultaneously because it makes a difference. Well, if I know who wants to buy what and who wants to sell what, if I make my consumption plan knowing that in advance, well, I know what's feasible, what can be done. That's something different than solving all the optimization problems simultaneously without knowing what the others will be planning to do. So we have several interdependent and simultaneous optimization problems. Well, for something to result from this bundle of optimization problems, which can be carried out, which can be put into practice, then that requires that we have consistent solutions. To several interdependent and simultaneous optimization problems under constraints. So most of this course will deal with that. Now, if we go one step further, as we have seen in the pure exchange economy example, in game-like situations, the problem is the following. There are more than one party. Well, one-person games, they're nice puzzles, but they're not interesting for economics. Robinson Crusoe is not interesting for economics. But the outcome, that will depend upon the joint action of all the agents. I can decide about my action, but that will by itself not determine what will materialize. What materialize will depend upon the joint action of all the agents. So if I know what the others will be doing, if I have information in advance about what the others' actions will be, then I can, that's an optimization problem for me, I can find an optimal response, a best response to that. But if I do not know, then I have to go over all possible joint actions of the rest of the world and find my best response to that. So I will have to solve a bundle of optimization problems. Moreover, if the outcome is to last, to persist, is stable, then this means this takes us to the generic definition or description of an equilibrium. That is, well, that will be a configuration where the underlying joint action is such that no one has any reason to change his or her action, to deviate from his or her action at that bundle, in case everyone else sticks to his or her action at that bundle. So we have the notion of an equilibrium. Well, again, we have whether an equilibrium exists or not. Well, if it exists, whether it's unique or not. Now here, the main mathematical tools that will be used are as follows. You consider the best response correspondences of all the individuals, the individual best response correspondences. Then you conjoin them into a collective best response correspondence. If that has a fixed point, that turns out to be an equilibrium. So here we need fixed point theorems. Moreover, if you deal with best responses, they're usually not singleton valued. Given what the others will be doing, I might have several best responses. Well, I'm indifferent between those, but that's a set. So here, set-valued functions, to which we refer as correspondences, they turn out to be important. And each fixed point theorem has to do with some kind of continuity. So we're interested in continuity of correspondences, of set-valued maps. That is, correspondences and continuity of correspondences. The part of the economy that I have been referring to, well, that had always, well, if I decide to consume this much of that good, that much of another good, and so on, these are all private goods. But you also have public goods. Well, with private goods, the price is the same to all, but the quantities consumed, they differ. They differ about what the individuals separately wish to have. Here, the most sheer or the purest, one of the purest public goods is national defense. Well, national defense, well, we might all have different preferences about what the level and content of national defense should be, but it will be the same to all of us. I cannot buy my own national defense. You cannot buy your own national defense. The quantity to be produced, available to be consumed, that will be the same for all. But the price will be different, because that will actually be financed by taxes and so on. Everybody's contribution will be different. But here, the question is quite different than the optimization problems in this world. Now, why? Well, there might be several possibilities, alternatives for a particular private good, and we may have different preferences. We may rank them differently. We may prefer different alternatives to different alternatives. Then the question becomes how to produce a social will out of those individual wills. How to aggregate those individual preferences into social preference. Or, being less ambitious, well, we don't need to socially rank all the alternatives. We can only focus on the top class of that, what's to be chosen. So that leads us to the notion of social choice rules, which are, or social welfare functions, which act as aggregators of individual preferences into either a social preference, in the latter case, or into a social choice, in the former case. So this again requires its own mathematics, but properties of social choice rules, social welfare functions, possibilities and impossibilities of aggregating into individual preferences into social preference. That's what this part deals with. It will not be this semester, next semester, but another big class of problems which economics deals with is the following. Well, here, mostly we have talked about single-shot events. You choose something, and you put that into practice, and it's over. But you can also model, and that's more real-life similar, you can also model what happens in a stage-wise fashion. Well, at some stage, you take decisions, you take some actions, something materializes, but that determines what the initial conditions in the next stage will be. Then you pass to the next stage. Well, if there's a next stage, if the stages are discrete, then we refer to that as a discrete time modeling. But that might not be the case. You might have continuous time. So the time difference between stages that may go to zero, well, in that case, we have continuous time. Now, the transition from one stage to another stage, in the discrete time case, that's governed by a difference equation in most of the cases. And in the continuous time case, it's a differential equation. So this much we have considered mathematics from the viewpoint of what kinds of tools, useful tools it provides for economic analysis. And this actually covers the topics. Each topic we will consider is either a preparation or the result itself, solving which is helpful to solving some kind of problems which is put already on the board. But is that all? Well, are we interested in economics? Are we interested in mathematics and in economics education? Are we interested in mathematics only for the sake of tools it provides? Well, in order to answer that, let's ask the following question. Well, what is science? Be it a natural science or a social science, what does it deal with? Well, science can be summarized in the simplest terms as our systematic and general knowledge about objective reality. That reality might be the nature, live nature, unlive nature, or society, and so on. Okay, but here, particular observances of particular phenomena and description of that, that's neither general nor systematic, nor does it allow us to make predictions. General and systematic knowledge is needed to make some predictions, which again will be tested by objective reality, whether the prediction turns out to be true or false. So the main objective of science is to go beyond the outer appearances of things and discover the causality relations. Which underlie, which explain the change, the evolution of phenomena, and allows us predictions. Now, how can we discover, how do we discover in science causality relations? Well, that's the place where this happens is theory. Just by empirical considerations, without any theory behind it, well, then everything is in itself, so we cannot make any generalization. Generalization can be made, well, once you discover the causality relations. How do we do that in theory? What's theory? Economic theory, physical theories, chemical theories, and so on. Well, what you do is you try to reconstruct, to make a mental model of what's happening in objective reality. And the main building block of doing that, they're concepts. You use appropriate concepts and you try to reconstruct mentally what's going on, a model, what's going on in objective reality. And that construct, which we refer to as a theory, that allows us to analyze causality relations. That is, what implies what? Implications. What's the reason? What's the outcome? And in what sense and to what extent does the reason affect the outcome, and so on. So these are implications, but mathematics is the theory of implications. In mathematics, all theorems tell us, each theorem tells us, well, what kind of conditions, when they are satisfied, imply what kind of conditions. So here, in theory, it is not just as a tool the content of what mathematics deals with, but the approach of mathematics, which is useful to constructing theories and getting outcomes, implications, which are to be tested, and when they get tested, they actually are classified as scientific truths. The approach is important here. Well, if that's the case, now so far we have started from economics, and then what economics aims at, what it does, and what's the use of mathematics in that. Now let's start from mathematics. What's mathematics? What does it deal with? Well, we have just focused on what's useful in mathematics for economics, in terms of tools, in terms of approach, and so on. Well, or in order to go one step further, is mathematics a science? Well, what does science do? Well, we said it deals with objective reality, and it tries to discover the causality relations underlying the evolution, the change in phenomena in the outer world. What does mathematics deal with? Well, it deals with numbers, for example. Numbers are concepts, but where does the origin of numbers lie? Is it a sheer product of human brain, of human intellect, or does it have an origin? Did it come into being during humanity's entire life, just from the brain or from something in objective reality getting reflected into the brain? Well, no matter what kind of and how complicated a concept about numbers you introduce now, well, the origin is counting numbers. You have 2 trees, 5 stones, such and such. In fact, calculus, well, that's the science of stones. I mean, that's where numbers came from, or geometric figures and so on. Now, whatever concept in mathematics you take, no matter how indirect its relationship to the outer world is, all the concepts have the original addresses in the outer world, in nature, in objective reality. So they're all abstractions of notions which have been formed via the reflection of outer phenomena into human intellect, but they have their origins outside. That's one thing. In science, what's the yardstick of truth? How do you decide in physics, in economics, in social sciences, in chemistry? How do you decide whether a finding reflects the truth or not? You test that against reality. Well, in cases you can make controlled experiments, you make that, but sometimes you cannot make that, but then you make observations. Well, if you have a historical prediction, a forecast, then history tests that. But it's too late. Well, if it's false, and if it turns out to be false, well, to learn, to find out about its falsity, since history tests that, well, it might be too late in that case. But you test that against. How do we decide whether something is true or false in mathematics? That will be very common in this course. It's proof. Given a statement, proving that statement, that means starting from a collection of statements which either are assumed to be true without any proof, axioms, or which have been proven before. If you can form a sequence of deductions starting from that bundle of known statements, if you can reach the statement, which is the claim, well, then you say, well, we have proven that statement, and that's true. You get a theorem. But what about the deductions, the sequence of deductions you make? What must they obey? They might be consistent with the rules of logic. Logically, each step that should be deducible what precedes it. But what's logic? Well, the same question. The mathematical concepts we have asked, well, are they a sheer product of human brain, or did they come into being via the reflections of the outer world into human intellect? What about logic? Is it a sheer product of human brain? Do we get born with a chip of logic which gets activated as we grow up? Is that the case? Or the rules of logic, are they derived from what we observe? In mathematical concepts, as well as in the rules of logic, the value added by human intellect is very large. No doubt about that. But all the logical rules are deduced from objective reality. I observe, well, when it rains, without any clouds, it does not rain. There are always clouds. But there are cases where clouds exist, but it does not rain. Then the relation between the existence of clouds and raining, I deduce, is the following. Clouds are necessary for rain, but they are not sufficient. And we make that observation all the time with all the phenomena that we observe. Well, kids are not born with logic. Logic is something which gets acquired afterwards in our experience, in our living experience. In fact, that's also true for the development of mankind. Well, anthropologists, well, there is no logic in some primitive tribes. That's different. It gets actually matured with time, with civilization. And well, an indirect proof of that logic is acquired afterwards. People do not get born with that is, well, that some people never can acquire that logic throughout their life. So that's another indirect proof of that. So mathematics is a science at a different level. It reflects, when I say it's a science, then it reflects the relationships that mathematics reflects. They originally are abstractions from the relationships which exist by themselves in objective reality. Right? So that's why mathematics is so useful in building theories in most of the sciences. Well, in some sciences, that's at a very low level, but still. Well, Einstein says that nature is mathematical, observing how useful mathematics has been in building physical theories. But I guess the relationship is rather the other way around. it is not the case that nature is mathematics. More, it is the case that mathematics is natural, since it is derived from nature, both its notions and the rules it obeys, the rules of logic. So we have two aims. One is introducing powerful tools, and of course, when they can be used and when they cannot be used, we will be very precise about that. That will be crucial. But we're also interested in the contribution of mathematics via the maturity it provides, it ends up with in dealing with concepts, the approach of mathematics, mathematical maturity. So we will actually be proving everything, and we will try to develop our ability, our competence, how to prove things. Okay? So it's twofold. It's not just a toolbox matter, but that also helps using the tools in the toolbox in a very efficient manner. We will be interested in both. Now, that was quite general. That's the introduction. Now here, when we start with doing the job, we'll start with doing the job next time. But here, we will be dealing with Euclidean, finite dimensional Euclidean spaces. Well, why Euclidean? Well, that's Rn. Our objects will be n vectors. Vectors with n components. N could be n. Well, the simplest case is when n is equal to 1. That's the real number system. We will start with the real number system. Then we construct the n-dimensional version of that. Y is referred to, and we will impose different structures on it. What's Euclid famous for? For geometry. So, well, it is actually the structure of Euclidean spaces which allows expressing and dealing with and analyzing geometric questions. That's why Euclidean spaces. But that's chapter 1. That will be elementary topological properties of Euclidean spaces. Now here, as I said, this Euclidean, that will be based on the geometric structure that will impose on Rn. But what topological is, that's the main thing that we will be dealing with in here. Let's leave that for the time being. So 1, 1, that will be the real number system. Now you have been dealing with the real number system, well, since we have been dealing with that since we started the elementary school. Okay, so you start with counting numbers, then you have the negatives of them. 0, well, the positive integers, we refer to them as natural numbers since they're counting numbers and they come from nature. But we have different structures imposed upon reals. For example, we add real numbers. Addition, that's an algebraic operation, an algebraic binary operation. It takes two real numbers and produces a real number out of that. It's a function on R cross R on pairs of real numbers. It associates with each such pair a single real number. It obeys different properties, different rules. For example, A plus B and B plus A are equal. So that's commutativity, as we refer to. Or if you have three real numbers, A, B, C, if you add up A plus B and then add that sum with C, well, you get the same result when you do that first B and C, add them up, and their sum with A. That's associativity. There is a neutral member which, when added to other reals, does not change the real. That's 0. And every real number has an additive inverse. If you have A, if you add that with minus A, you get 0. So these are the rules. But we also have multiplication, which obeys similar rules. A, B, B, A, they're the same. Well, A, B, C, it does not make any difference how you group them. There is a neutral element there as well. If you multiply any real number with 1, you get the real number itself. What about multiplicative inverses? For each number, does there exist another number? For each A, is there an A prime such that A times A prime is 1? There is one exception to that. If A is 0, there is no. Okay, so these are almost the same, but a bit different than the properties. But if addition and multiplication state as separate mathematical structures imposed upon R without having any interconnection, that we do not like in mathematics. But what's the connection between addition and multiplication? How are these two separate structures? They're both functions on R cross R into R. In one case, the pair AB is taken to A plus B. In the other case, the pair AB is taken into A times B. Okay? What is the connection? That's something which we learned in elementary school, the connection. It is the distributive law. If you have three real numbers, this is equal to AB plus AC. This is the connection which connects the two structures. This, of course, is derived from nature again. Okay, so if you just consider counting numbers, and in elementary schools, okay, you take, well, here, stones, A stones, B stones, C stones, then AB, that will be, A times B stones. You clone that A times, but you get the same. But if you abstract that as a binary operation both, and extend that to all reals, not the counting numbers, then this is the main connection. So this addition and multiplication and their properties together with this interconnection, we will refer to that as the algebraic structure of reals. What other structures do we have? This is what we learn in elementary school. Well, given two real numbers, x, y, there's this so-called trichotomy law. Either is x larger than y, or is y larger than x, or they're equal to each other. So we have an order structure. Is the order structure related to the algebraic structure? Now, for example, if A is larger than B and C is positive, then this implies AC is larger than BC, or A plus C is larger than B plus C. You have several such relations which actually interconnect the algebraic structure with the order structure. Okay? We will take the algebraic structure and the order structure as given to us. We will be free to use everything we know from before about those. But does that make the real number system? Do we know everything about reals when we know the rules this algebraic structure obeys, the rules this order structure obeys? I will close by asking the following question. In calculus, you don't deal with this algebraic structure. You really don't deal with the order structure as well. If you are to name just one concept which is central to calculus, what would it be? One means, well, you're not allowed to say derivatives, differentiation, because you also have integration. That makes two concepts. But what's common about integration and differentiation? They're both limits of certain things. The notion of limit, that's what's central to calculus, and it cannot be deduced from these two structures. And it is that notion of limit, the extension of that, the generalization of that, which will lead to this topological structure. But we will deal with that. We will construct step by step the topological structure of the real number system first, and then extend that to the n-dimensional case. I guess we can stop at this point.